Okay, so welcome. Did you have something you want to say?
You were for being in class. What restrictions do you find yourself?
Let me just say, welcome to Math 389 Advanced Analysis, Lecture 21. Before class, we were talking about proving things either in general or with additional constraints to make things easier. And so I was assuming that the moment generating function exists in a neighborhood about the origin. Given that moment generating functions don't necessarily have to exist, that is, of course, a big assumption. Now, the Cauchy distribution, for those of you who know it, does not have a mean, but you could argue it has a mean 0 because it's symmetric. It definitely does not have a finite variance. I can look at a tweak of the Cauchy distribution. I can look at 1 over 1 plus x to the 4th or x to the 6th. And in something like that, it now does have a mean and a variance, but it doesn't have a moment generating function that converges. So I could look at sums of these modified Cauchy distributions. And if you know complex, you can actually write down in nice closed form by doing contour integrals what the normalization constants are in terms of pi. It's wonderful. All right. So what I want to do today is I want to talk more about strange examples and limits. And so I had mentioned before, how many of you have taken a class in abstract algebra? All right, because the video is not on, I will have to say for the record, I have not. I never was able to fit it into my schedule. I had to learn it over the summer. So as a nice exercise, try to come up with a set that is almost a group. I want it to have a left inverse and a right identity. Or I'm sorry, left identity and right inverse. And so can you come up with something like that? So obviously what you want to do is you want to create a multiplication table. And so the first thing is you assume you have just two elements, 1 and x. And then if that doesn't work, you have 3 elements, 1x and y. And so see if you can come up with this. So, as homework, and there's not that much homework that's given, try to see if you can come up with a set that's almost a group. But it's not enough to just have a left identity and a right inverse. But it is enough to have a left identity and left inverse for everything. Okay. The next one, which I had mentioned, was you're trying to integrate from minus infinity to infinity of sine squared x over x squared dx. And so the way you're supposed to do this, how many of you have taken complex? That one I'll at least raise my hand for. Okay. So some of us, and I know at least one person in Zoom has taken complex as well. So if you've taken complex, you can write sine as e to the ix minus e to the minus ix over 2I. You expand things out, you do contours, you do a little bit of profanity, because unfortunately, you've got to be careful how you split things up, and you've got a singularity on the contour, so you have to have a little epsilon dip. It's a little bit of a pain. What I noticed is if you let u equal and dv equal, so I want dv to be x to the minus 2 dx and u to be sine squared of x, then du is 2 sine x cosine of x, v is negative x to the minus 1. But what is 2 sine x cosine x? Who remembers their trig? Sine 2x. So this integral is just uv at minus infinity to infinity minus the integral from minus infinity to infinity of v du. Well, since v is negative 1 over x, the boundary terms vanish. The minus signs reinforce, and I get the integral from minus infinity to infinity of the sine of x over x dx. I'm sorry, sine of 2x over x dx. Well, I can multiply by 1, so I'll put a 2 here and a 2 down there. And then if I let u equal 2x, this just becomes the integral from minus infinity to infinity of sine of x over x dx. So really what we're saying is when you integrate like this, you can just cancel the 2's. Doesn't always work, but it makes it a much easier contour integral to do. And so I was a bit of a smartass and made a remark like this, because you can actually evaluate this using some real analysis techniques. So if you think about what's going on with sine of x over x, if I put in absolute values, the integral is infinite. So if I try to just integrate from minus infinity to infinity of sine of x over x dx with absolute values, that's infinite. And so as soon as I see an infinite, I am now worried that the integral does not exist, because I want the limit as a and b go to infinity of the integral from minus a to b of f of x dx to exist independent of the path. And this is why the Cauchy distribution is so bad. Because if I look at the integral from minus a to b of 1 over 1 plus x squared dx, if a equals b, I get 0. If b equals twice a, I basically have the integral from a to 2a of x over 1 plus x squared dx. That's basically just the integral from a to 2a of 1 over x dx. So that's just the natural log of 2a minus the natural log of a, which is the natural log of 2. And by arguing similarly, I could make it natural log of 3, natural log of 4, whatever. So the limit depends on how we get there. This is the danger of having integrals where the absolute value is not finite. The integral of the absolute value is not finite. But for sine of x over x, even though that integral is infinite, this still makes sense. The limit as a and b go to infinity from minus a to b of sine of x dx is independent of the path. And so, again, since we were talking before class about, how general do you do things? There's a difference between a necessary condition and a sufficient condition. Anybody see Dodgeball? There's a nice line about something that he does that's not necessarily necessary. Can somebody give me a necessary condition to win the Super Bowl?
Beat the other team in the Super Bowl.
Okay, is that a sufficient condition? If you beat the other team in the Super Bowl, will you win the Super Bowl? Yes. Right? So beating the other team is definitely a sufficient condition. Is it necessary? Yes. If you don't beat the other team, you're not going to win the Super Bowl.
That's true.
Give me a necessary condition that's not sufficient to win the Super Bowl. It's necessary that this happens, but it's not sufficient. If you want to get on Professor Blackwood's bad side, you can mention this.
Get to the Super Bowl.
Get to the Super Bowl. So the Buffalo Bills made it to 4 consecutive Super Bowls without winning. And do you know how they're able to get T-shirts so quickly to the Super Bowl winners? They make up both. So the joke is that there are these questions of what happens to the Super Bowl shirts for the team that lost. Nobody wants them. So the joke is that they donate them to poor people all over the world. And you just imagine all these Bills fans, they did it 4 years in a row. You have the whole collection. So it's sufficient. It's sufficient to score more points, and it's necessary. It's necessary to make it to the Super Bowl, but it's not sufficient. So I was asked, what conditions am I using in probability this year to prove the central limit theorem? For what functions? If we know that the integral of the absolute value is finite, then we know that everything is finite. It doesn't matter how a and b go to infinity. But it turns out that that is not necessary. It's sufficient, but it's not necessary. And so if I give you something like the sine of x over x, even though the integral of the absolute value is infinite, it still makes sense to integrate without the absolute value. And the reason is, what is the largest value of sine of x over x?
1.
1. And where does that value take? Where do we get that value?
At 0.
At 0. So we know it starts at 1, and then it goes down, and then it comes up, but not as much, and then it goes down, and it's something like this, and it's reflected on the other side as well, right? So when you look at this, what theorem from analysis does this remind you of? I'm sorry? How squeeze? It's one way to interpret it. So what I can do is I can look at the area under the positive peak. And then I'll do it like that on both sides. And then I'll look at the negative peak over here and then the positive peak over here. This is not drawn to scale. And if I look at these numbers, this is a decreasing in absolute value, alternating in sign. So the sum converges. So this is a nice theorem from analysis. If I have a sequence of numbers of decreasing absolute value, alternating in sign, then the sum converges. And so I could do this also on the other side as well. And so we know that the sine of x over x has to have a finite integral. What it is, I don't know. When you look at it initially, you might have some concern because what does it look like near the origin? Well, actually, it's fine because near the origin, sine of x looks like x. So this is a great lesson on, so it's sufficient for the integral of the absolute value to be finite, but not necessary. And this is one of the biggest questions you have in your career as a mathematician. How general do you want to prove things? When I was in college, I wanted things proved in as much generality as possible. Why would you assume something you don't need to assume? Prove it with the least necessary. Then I went to grad school and I actually started to do math to use math to do things that I cared about. It's like, well, of course my function's infinitely differentiable. And so then you start to say, well, what am I going to use it for? And again, it's nice when you have a friend who's an analyst who can prove things in great generality, and then you can just pull that result in as you need it. Okay, so let's start looking at some interesting possibilities. Just so it's stated here, Fubini's theorem, which we've looked at before, the integral of f of x, y, I can switch the orders of integration if the double integral of the absolute value is finite. And again, that may not be the weakest condition under which things are true. I'm sure we could take the example we just came up with and smear it out so that things would be fine. And the integral of the absolute value would be infinite. But what's really going on is if the integral of the absolute value is finite, then from some point onward, the sum of the absolute value of the tail elements is small. And then if I reorder things, eventually everything that is left over is also going to have to be small. And so this gives you some sense as to why we have conditions like this. So no matter once you reorder things, at some point onward, everything is going to be small because I know the tail is small because the integral of the absolute value is small. But this leads to the questions of, well, how do I know stuff like this is small? So let's look at some questions. If the sum of non-negative terms is finite, must the terms tend to zero? So here we have the sum, say n goes from 0 to infinity of an is less than infinity, an is greater than or equal to 0, must the limit as n goes to infinity of an equals 0? What are your thoughts? How many people have taken real analysis? I think everybody should have taken real. Yes. What are your thoughts? If the sum is finite.
Yeah, it has to go to the,
okay,
it's the tail of the series.
So yes. So tail must go to 0. But how do you prove it?
Well, you could say that an is, let's say it tends to some L that's greater than.
Okay, so we don't know that the ANs must converge.
Okay.
Well, we can use quotient condition.
Okay, so that's getting to be involved. I mean, can we have like a lower level thing?
Basically for all epsilon there exists.
Good. If it doesn't converge,
Oh.
then for all epsilon, there exists infinitely many n such that an is greater than or equal to epsilon, because we know the an's are non-negative. And since they are greater than or equal to epsilon infinitely often, if the sum of the is finite, this is basically saying the sum converges. You know, or the other way of looking at it is we would get infinitely many epsilon boosts, the sum would diverge. So sum diverges as sum of non-negative numbers and get epsilon infinitely often. So it's not too bad to get that the terms have to go to 0. Okay. What if instead of a sum, what if I say the integral, oh, so it re-scaled things, so put it on 2 lines. If the integral of a non-negative function is finite, so now we have the integral from, let's say, I'll do 0 to infinity of f of x dx is less than infinity, f of x is non-negative, must the limit as x goes to infinity of f of x equal 0. So function integrates to a finite number, it's non-negative, must the function be converging to 0 in the limit?
Yeah, we can break the function into intervals, and then each of the, so like we can break it from like interval on like n to n plus 1, and then this will form a series as well. Oh.
This is probably one of the most incorrectly assumed theorems in undergraduates. I may be getting it slightly wrong. I think Einstein once said, no matter how many experiments you have confirming my predictions, that's not a proof. But one experiment that sees something different is enough to disprove it. I just need one counterexample. And so, again, one of the things that's nice about this class is there is no Math 390 that builds on 389. The goal is to teach you how to think, how to attack new things. Now that you know that the answer is no.
Oh, okay.
Okay. So what's your function?
If I say f of x equals 1.
Okay, so if the function f of x is 1, then the integral would be infinite.
Oh, wait.
And if you have the function is 1 up until some point when it becomes 0, then it works.
If we have like many points that are, let's say,
Good. So one thing is, whoops, I'm still in this. Never said continuous. Right? So just say f of x equals 0 unless x is in n, and then it's 1. Okay? So assume it continues now. If you have an exam and you have a problem that has parts A, B, C, and D, what is often useful to do in part B? Assume part A. So what did we just do a moment ago? Oops. We just looked at a sum of non-negative terms, right? So we know if we have a sum of non-negative terms is finite, then the terms must be tending to 0. So let's see if maybe there was a reason that was done right before doing this. So here is n, here's n plus 1, here's n plus 2. And let's take intervals of size 1/2. So here's n minus 1/2, here's n plus 1/2. So let's let an be the integral from n minus a half to n plus a half of f of x dx. What do we know about the, and these are going to be non-negative. So what do we know about the ANs? They have to go to zero. We know that the limit as n goes to infinity of an has to go to zero. Because we just showed, we know that the integral of f is finite. And if we let an be the integral from n minus a half to n plus a half, then we can break the integral of f into these blocks. Each block is non-negative, right? So we know each of these blocks has to go to zero. That's not the same as saying the function has to go to zero. It just means the integral of the function over intervals of size 1 has to go to zero. Can you give me an example of a function that's going to have a small integral on one of these blocks? Or give me a sequence. We need the sum of an to be finite. So give me a choice for an.
1 over x squared.
Okay, so let's try an is 1 over n squared. So I want to find f such that the integral from n minus a half to n plus a half of f of x dx equals 1 over n squared. Okay. And ideally, we might want it such that f of x does not go to 0 for all x. So if it's not going to 0, maybe f is getting large in small regions and small most of the time. So I want, let's so here is n minus a half, n plus a half. Any thoughts about how large I should have f be at n? There's lots of ways you can do this. I'm sorry?
1 over 2.
Okay, so we could make an f really, really large at n. You said it was 2 to the n? Or 1 over 2 to the n?
Just 1.
So we could just make it equal to 1. And then over what width? We can do a triangle. Well, we want to get 1 over n squared, right?
2 over n squared.
So we would go to n plus 1 over 2n squared over here, and then n minus 1 over 2n squared over here. And then if I look at that, the area of that triangle is going to just be 1. If I wanted to, I could be even more drastic. And I could go up to n and have things of size like 1 over n cubed. And it would still give me a 1 over n squared. So I could actually make the function explode if I wanted to. So just because the integral of f is finite does not mean that f has to be going to 0 pointwise. This is one of the most common mistakes people make. And I think the reason they do it is because it's true for sequences. If I give you a sequence of non-negative terms, then the terms have to be tending to 0, yes. But if I give you an integral, the function can be getting larger and larger and larger, so long as it's on smaller and smaller and smaller sets. And so it is possible to give you a function which has finite integral. Okay. So the next question, if the sum of non-negative terms is finite, must the sum of the rth powers be finite? So an greater than or equal to 0, sum of an is finite. What about the sum of an to the r.
What is R? Is it integer?
I have not said what r is.
R is greater than 1.
Okay, so it's true. Whoops, sorry, you spelled true. It's true if r is greater than or equal to 1. As in that case, 0 less than or equal to an to the r less than or equal to an, and it's the comparison test. What if r is less than 1?
So it's going to 1.
So what could happen if r is less than 1? Then an to the r could actually be greater than
That's the rate of
an. So at this point now, we either have to prove that it's always going to be finite, or you have to give me one sequence where it's not.
I mean, we can just take a n to be 1 over n squared, and then r to be 1/2.
Okay, so that would be a specific value of r and a specific value of n. Or a specific value of r. Can you do any value of r less than 1?
I think where.
So if I give you 1 over n to the 1 plus epsilon, that will converge. And then an to the r would be 1 over n to the 1 plus epsilon times r. So I want 1 plus epsilon times r to be less than 1.
Yeah.
And epsilon greater than 0. So 1 plus epsilon is less than 1 over r. So 1 minus 1 over r. Have I done this properly?
Do we want R to be positive?
Yeah, we want r to be positive. Did I do things in the wrong way? So if 1 plus epsilon is, so if epsilon is positive, then that sum is going to converge. But now if r is less than 1, I can make this exponent less than 1. So I divide both sides by r. Oh, there's a negative epsilon here. All right, there we go. All right, there we go. Now things are good. So now when I multiply through by -1, I get epsilon is greater than 1 over r minus 1, which is going to be yes. So r is less than 1. So when it's 1 minus r over r. So that is,
I think the sign should flip.
Yeah,
what I missed?
it's like you just like swap both the sides.
Oh, sorry, I swapped the side. Right, sorry, thank you. Let's go slowly. And okay, so I'll put the epsilon here. So I get epsilon is less than, and I move everything over 1 over r minus 1. So epsilon is less than 1 minus r over r. Okay, good. So good. So if I choose that for my epsilon, then I will have a sum of an of non-negative terms that's finite. But if I raise it to the rth power, it will be infinite. So the answer here is a resounding no. And this is not as surprising, so I'm not going to put it in fancy, strange, futuristic font. But when you first looked at it, did it seem reasonable? It depends what you think r is,
Yeah.
right? I mean, if you think r is a positive number that's greater than 1, then yeah, it's reasonable because it's true. And so one of the hardest things is to keep track of what are people assuming, what are people implicitly assuming. I don't know if I shared the story where I gave a graduate student a heart attack on his thesis. So he was working with a colleague of mine, and my thesis generalized some of the work he had done. Because I worked in the area, you know, he showed me the thesis and he was very proud as he showed it to me. And I looked at it and goes, oh, it looks really interesting. Do you know half your thesis is wrong? And you go, what? And then I just let him sit for like a moment or two and said, you're using a paper by a certain person, and I know in that paper they say we assume K is congruent to 0 mod 4. If K is 2 mod 4, it follows similarly with an extra minus sign. And so when you quoted a result, you forgot that there's an extra minus sign for half the cases. It takes less than 30 seconds to fix your thesis. For just half the cases, you just put in a negative sign. But when he was looking at it, he didn't realize that that paper had assumed that K was 0 mod 4 throughout. Whenever I write a theorem, I always like to restate what are all the assumptions I'm making. People often theorem shop. They look through various collected works, collected papers. They try to find something that can be useful to them. Oh, good, I found it. Now, you should read all of the paper up until the statement of the theorem. Sometimes papers say, we assume throughout the following, and they don't explicitly remind you of that in the theorem. I think that's terrible. Even if it's a common assumption, you should be explicit and say, hey, we're assuming X. There was somebody who had proved the Riemann hypothesis, and the referee I had could not find the mistake, so I had to go through it carefully. I couldn't find the mistake. I eventually noticed he was using a result from a book, and the chapter he used, he quoted the theorem correctly, but in that chapter they assumed the Riemann hypothesis.
Nice.
So yes, you used the theorem correctly, but the theorem requires the Riemann hypothesis. So I'm doing this because I want you to laugh now. I don't want you to do this when you're doing your own work. So really think about these examples. Think about what are you just implicitly assuming? I mean, if you go back to some old classical geometry, people just implicitly assume certain axioms had to be the case. Well, they don't. You can have different structures, so be very careful. So over here, I never explicitly said what R was. That's the whole point.
Like, would it make conceptual sense to explain this result?
So I mean, the conceptual result to me is that if we're in this case when R is greater than 1, we're making things smaller.
Yeah, I mean for the less obvious case.
For the less obvious case, we're making things larger.
Yeah, and I would say maybe like since you need at least like power decay for the series to converge,
right,
then you cannot counteract that decay with power.
Well, so we're making things larger in some sense by a fixed exponent.
Yeah.
And so as long as I choose my series appropriately, I can have my series converge, but with not that much wiggle room. Now, if I gave you a better series, if I gave you 1 over n to the 50, then if I was really small, it's still going to converge when I raise it to the nth power. But I can have something that's just barely converging. And so now when I raise it by the nth power, now I'm in trouble. So it's really good to internalize these counterexamples. What do you think I'm going to ask you next?
Something else about convergence.
Right, but what?
Integrals.
Yeah, integrals, right? We did a sum, then we did the same version of that problem, but for an integral. We just did the sum, so now I'm going to give you the integral version. If the integral of a non-negative f of x is finite, must the integral of f of x to the r be finite?
My assumption is no.
No. Right? Can you give me a proof?
Same thing with the triangles before.
So we should basically be able to modify the triangles before, or since we know that it fails for the sum, just take f of x to be on intervals of size 1, an.
Yeah.
So one proof, oops, all right, we'll do a fun proof. So we could do f of x have f of x equal an for n minus 1/2 less than equal to x strictly less than n plus 1/2. So our example from before is going to be more than that. Okay, what was your thought?
Could you remind me what convergence is?
What convergence is?
Yeah.
So something converges to a value L if given any epsilon. From some point onward, I am within epsilon of that L.
Nice of you for saying that much.
So you can't converge to two different values because the two different values are separated by some amount. Let's call it delta. If I choose epsilon to be less than delta over 10, I know I can't be simultaneously close to two things. So if I converge to at most one quantity. And what it means is it's a game. You know, I want to be within 1 over a billion, fine. If you choose n this large from all n, at least that large or larger, you're within 1 over a billion. I changed my mind. I want to be within 1 over a trillion. Fine. Now I'll choose n to be this large. As long as you're at least this big, fine. I changed my mind. I want to be within 1 over a quadrillion. I hate you. Changing again. We can keep playing this game. Okay. Now there's other things you could do. We could play games. And again, the reason I want to do this, not to scale, here's n plus 1, here's n minus 1, is I care about techniques. Here's 1 over 2 to the n, to the, we'll call it n plus 1 over 2 to the n to the delta, and here's going to be n minus 1 over 2 to the n to the delta. Oh, I apologize. Now I realize what you were doing. I'm sorry. It's my fault because I apologize. I will pause it and explain what's going on. That was my fault. So I'm going to resume recording. And so what we could do now is I love having free parameters to come up with counterexamples. So I don't know exactly what I want. Let me move over into the delta. And I'm putting over the 2 because I want to use a triangle so it's continuous. And then that's going to give me the 2 to compensate for the fact that the triangle has an area of 1/2 base times height. How high should my function get? N to the what? No, because then no. It's not delta, it's not 2 delta. What should it go up to? I want free parameters. What should it go up to?
Something delta.
So you could do some function, you could do f of delta, or just do another letter sigma. Give yourself some freedom. And so now I would want, the sum of n to the sigma over n to the delta to be finite. And I want the sum of n to the sigma r over n to the delta to be infinite. And so if I do something like that, I can see, okay, I need sigma minus delta has to be less than -1 for it to converge. So I need sigma to be greater than 1 minus delta. We know delta is going to be less than 1 because I live in some small interval like that. So that's not a big deal. And now what I would want is I would want sigma r minus delta would be greater than or equal to -1. And so I'm trying to find, I've got some freedom with sigma and delta. Now, if you want, to some extent, I can always adjust sigma by putting in a multiplicative factor of delta. Because when I multiply them together, that's going to come into play. Right? Is that correct? Am I allowed to do that? Yeah, because delta is fixed. I can always just make sigma equal to, say, tau times delta. I just give myself that extra flexibility. And so now if I want to figure out, yeah, I have to choose either sigma or delta, and then I get the other one. So I would get sigma r is greater than or equal to delta minus 1. So I would need r to be greater, so I would need sigma to be greater than or equal to delta minus 1 over r. But I also need sigma to be less than, oh, sorry, I also need sigma to be greater than 1 minus delta. So I need to play games like this to make sure both of these happen. But I can construct things so that a function has a finite integral, its integral squared is finite, its integral cubed is finite. You know, all that's going to be okay. So for instance, if I look at something, so, you know, here's n, and maybe this is going to be of size 1 over n to the 2025, and I go up to height n, then the integral of, you know, f of x dx from 0 to infinity, it's going to be finite for, if I'm going to raise this to the rth power, for r less than 2024. And then once r breaks 2024, then the integral would be infinite. So these give you just some idea of how to come up with, you know, whole slews of counterexamples. Once you know some of these, it's not that bad. And then we'll end with, this was the one we were just talking about a few days ago. So consider the integral of exponential of m f of x as m goes to infinity. Assume f has a unique maximum on ab at x naught. Is most of the integral due to what's going on near x naught? And here's x naught, and the function takes on its largest value at x naught, and it takes on no other large values anywhere else. And so when you're trying to analyze this, you again, when conditions are not that severe, you have a lot of freedom to play with. And so we were talking about the central limit there when we talked about the Cauchy distribution. I love the Cauchy distribution. It's one of my go-tos. So I could say, let's take f of x to be a Cauchy distribution. But I said, well, I want things on the non-negative interval. So here, maybe I'll do things on the interval 0, infinity. All right, so I can shift the Cauchy distribution a little bit. 1 over 1 plus x minus 1 squared. Now this is going to have its largest value at x equals 1. Everything is well defined on 0, infinity. This does have some decay as we go off to infinity. Right? And so the largest value is clearly going to be at 1, and it's going to be the largest by a good amount. Now the integral here is going to be infinite. And so from any point onward, you're going to get a sizable contribution. So this is enough to show that no, the integral is always infinite, so it's really hard to talk about one place over another. We could put in some interesting factors. I could put in e to the minus x squared. And so now as x gets larger and larger and larger, it's going to be getting closer and closer and closer to 1. And so the problem is then modified that whenever you see an infinity is always a danger sign in mathematics. So what if you no longer have the infinity? So what if we have the interval 0, 2? Is most of the integral going to now be what's happening at 1? And so now, you know, we have the integral from 0 to 2, e to the m f of x dx. Here's 0, here's 2, here's 1, and the largest value is at 1. And now you've got to look very carefully. I'm telling you it has a unique maximum on 0, 2. The open interval 0, 2. So if I wanted to be problematic, what could I do? Yeah, something really funky at 0 and 2. What do you think I should have it be? I should have it basically converging to whatever the value is at 1. And so if you haven't seen this function before, this is a great function to look at. Have you seen this function? So it's 1 over e to the negative 1 over x minus a b minus x if x is between a and b and 0 otherwise. So you should see a function like this in real analysis. It's great. What happens as x approaches a from above? Well, if x is a little bit larger than a, x minus a is a very small positive number. B minus x is a fixed number, basically. So you have e to the negative 1 over small. That's e to the negative large, which is 0. So this function is almost 0 near a. Similarly, it's almost 0 near b. Okay, so this is a function that's really small at a and b. I can tweak it, right? Once we have something like this, we can tweak it without too much trouble. This is a plot of what it looks like. I love the warning Mathematica gives, really, please don't make me plot something like this. It's just so close to 0 down here. It's just crunching down, and Mathematica saying stop. Well, now we just play the games. So I look at the 1 over 1 plus x minus 1 squared, which was our Cauchy. And now I'm going to tweak it by putting in this fact, e to the negative 1. I'll choose a to be 0, b to be 2. So I'll get 2x minus x squared. And now when you look at the function, it has a unique maximum on the open interval at x equals 1. Near 0 and near 2, it's 1, and it stays 1 for a good amount. Now, if in some sense, it's got a larger amount where the function is somewhat large over here, but because m is huge, when you look at the integral of e to the m f of x dx from 0 to 2, because it's dropping off somewhat quickly around x equals 1, the contribution there is going to be much less than what's coming on from over here because it's dropping off much slower. So this is a really good function to cause trouble. And again, you should have stuff like this so that when people give you theorems, you can test them. You don't test things on nice examples. They'll work on nice examples, right? Levy takes something like the Cauchy distribution, which has infinite variance. If you can work it out on that, I'm now impressed. We'll probably do this later. The next is the fundamental theorem of calculus. How many of you, if your life depended on it, could give a rigorous proof with reasonable conditions on F? All right, we will definitely do this because there are a couple of things that bother me enough that I need to do something about it. So when I teach multivariable calculus, if you don't know what Green's theorem is, then I have failed you as a multivariable calculus professor. You need to at least know what Green's theorem is. If you can't prove the fundamental theorem of calculus, you do not belong as a math major. And I know this is being recorded. For those of you who are math majors at Williams who do not know the proof of the fundamental theorem of calculus, n is much greater than 1, where n is the number of faculty in the Williams math department. So it's okay that I may feel that you need to be able to prove the fundamental theorem of calculus to be a math major. Enough people feel otherwise, so you're safe. But you should be able to prove this. How can you at least see if the fundamental theorem of calculus is reasonable? What could you do? So it says the area under the curve is the antiderivative at b minus the antiderivative at a. So this is from Wikipedia. I don't like this version. What I like to do is the following. Define integral a to b of f of x dx to be area under y equals f of x from x equals a to x equals b. Then this area is equal to the antiderivative at b minus the antiderivative at a. That's how I like to say the fundamental theorem of calculus. The area under the curve is the antiderivative at b minus the antiderivative at a. Right, given that we're not going to prove it today, how can you at least see that it's reasonable? How can you test it? Okay, so what examples can you try? Nope. F of x equals f of x equals x is the second thing to try.
1, 1.
F of x equals 1, right? Start off with that, right? So let's see what the fundamental theorem of calculus is saying. So here's A, here's B. My function's identically 1. In this case, the antiderivative, or at least one antiderivative, is x. And so the area, which is b minus a, is equal to f of b minus f of a, which is just b minus a. We did a rectangle. All right, way to go, guys. Now let's do f of x equals x. This is a what shape? It's a triangle. I mean, I could do the more general ax plus b, but we'll just do this. And I need to find out, yeah. So this is technically a trapezoid. So I could calculate the area. So area is equal to 1/2 b times b minus 1/2 a times a, by just extrapolating and throwing away the green triangle. So I get the area is 1/2 b squared minus a squared, right? What function has derivative, or give me a function whose derivative is x. X squared over 2. And so now we get f of b minus f of a, yes, whoops, is 1/2 b squared minus 1/2 a squared. We did triangles. So we've proven that the fundamental theorem of calculus is at least reasonable for rectangles and triangles. It's nice, but it's really not that convincing proofs. These are really nice figures. What's the next figure we can try? F of x equals which polynomial? Well, we did 1, we did x squared. So now if you want to do the fundamental theorem of calculus for x squared, now what you have, I'll take a equals 0 just to make my life easy, is you now have a parabola. Do you know the area under a parabola without using calculus? So this is now a legitimate test. And now what we can do is we can do upper and lower sums. And we'll need formulas for like the sum k goes from 0 to n of k squared. And that we'll get by induction. So you can now use induction and stuff like this to provide a non-trivial example to support the fundamental theorem of calculus. It doesn't mean the fundamental theorem of calculus is correct, but I now have more confidence than just looking at rectangles and triangles. And I'll end with, I believe I've given you this before, 16 over 64. We've done this. 1/4. I'm sorry, cancel the 6's, it's 1/4. 19 over 95, cancel the 9's, it's 1/5. Right, 49 over 98, cancel the 9's, it's 4/8, which is 1/2. Therefore, 12 over 24 must be 1/4. And actually, if you really want to do this, what you do is you stop over here. So if somebody doubts, you've kept this in reserve. If you think this is absurd, consider Euler's prime producing polynomial, whose first like 40 plus values is always a prime number. Sometimes these patterns hold for a while before you see a contradiction. All right, so for Tuesday's class, we will prove the fundamental theorem of calculus, because while I cannot do requirements for the math department, I can at least do something for Math 389. And you should not leave a class titled Advanced Analysis without being able to prove the fundamental theorem of calculus. And this will allow us to talk about uniform continuity and review that wonderful concept. All right.